We just introduced the construction method, but we might still ask that whether all such congruence equations have solutions. Actually, we could prove a famous theorem which states that such congruence equations always have solutions by pigeonhole principle. This theorem is called the Chinese remainder theorem. Chinese remainder theorem said that for two relatively primes m and n and two non-negative integers a and b, when a is less than m and b is less than n, there must exist a positive integer x which makes the congruence equation group solvable. We just use a congruence equation group with three equations which are about divided by 3 divided by 5 and being divided by 7. Now for convenience, we only use two equations in the proof here, which is x equal to pm plus a. It means that x divided by m we have the remainder as a, and x divided by n we left b. Here, p and q are non-negative integers. This means that Chinese remainder theorem guarantees that after lining up differently like what Hanxin did, we could always find a number x which makes the equation group solvable by using the remainders. How should we prove it? Let's analyze it. Look at the first equation first. Assume that we could find n legal solutions. Consider n integers, which are a, m plus a, 2m plus a, until n minus 1 m plus a. A total of n integers. There is a common property of the n integers such that their remainders are a when divided by m, which satisfies the first equation. Here there are n integers. If one has a remainder b when divided by n, this means that we find the desired x. We have n integers here and we want to divide them by n. How many remainders are possible? Are there n possible remainders? This means that if all their remainders are different, we could find any possible remainder b. On the contrary, if there are equal remainders, this means that some value of b are not here. So we could use this idea to prove that when these numbers are divided by n, the remainders are different. Let's try to prove it by contradiction. Suppose that there are equal remainders. We could assume that when im plus a and jm plus a are divided by n, the remainders are equal, in which I is less or equal to j, and both of them are in the range from 0 to n minus 1. If their remainders are equal, this means that im plus a equal to qin plus r, while jm plus a equal to qin plus r. We could subtract these two equations and we get j minus I times m is equal to qj minus qi times m. This equation shows that the products of the two pairs of integers are equal. This means that n is a factor of j minus I times m in the left-hand side. Could it be true? We discovered that we require that m and n are relative prime in the conditions, so n couldn't be a factor of m. Meanwhile, let's look at the relation of j and I. J and I are in the range 0 and minus 1, and j is greater than I. This means that j minus I is smaller than n. So how could n be his factor? So we find that n and m are relative prime, so n must not be a factor of m. At the same time, ij are in 0 to n, so n must not be a factor of j minus I. So this equation is impossible. As it's impossible to have this equation, our assumption such that there are equal remainders is not true. So our conclusion is that for the n integer we constructed, when they are divided by n, the remainders are all different, and the number of remainders is counting from 0 to n minus 1, which is n. So no matter what's the value of b, as b is in the range of from 0 to n minus 1, there must be a number to satisfy x equal to qn plus b. This means that we successfully proved that all system of two congruence equations are solvable. Now, if we want to generalize it, the so-called Chinese random theorem actually tells us if m1, m2 until mk are positive integers which are pairwise relative prime, which means that their largest common factor is 1. I is not equal to j. I and j are from 1 to k, the system of congruence equations. X equal to b1 mod m1, and for m2, x2 equal to b2 mod m2, so forth, until x equal to bk mod mk. Now, for such a system of congruence equations, we could guarantee that their modules m1, m2 until mk are solvable by Chinese remainder theorem. This means that under the meaning of m1, m2 until mk, there exists x which satisfies x have the common remainders of bi mod m1, m2 until mk has a solution x.